I haven't quizzed you yet, this class, at least on the central limit theorem statements, so you probably can expect a quiz question related to that next time, as well as, again, one or two problems that are more focused on problem solving. So they will, I think, get harder as this material in general is getting harder too. On your homework due next time, you also have a Venn diagram problem that's got 3 circles rather than 2. And in reality, you theoretically can make Venn diagrams with 4 or 5 or 6 or 7 circles, though they get unimaginably complicated to try to draw. Okay? So 3 circles is typically the limit for most people. But again, just realize that when you draw these kinds of things, you want to think about the circles as representing, in this case, in this example, people who have certain kinds of pets. People who have cats only, birds only, excuse me, cats, birds, and dogs are represented by the entire circle. The intersections that you see here represent people who might have all 3, the intersection of all 3 sets, cats, birds, and dogs. People that are in here have cats and dogs but not birds. People that are in here have birds and dogs but not cats. People that are here have birds as pets only, no cats or dogs. We're not worried about other kinds of pets. They're sort of outside of this region. If you've got hamsters, for example, we're not thinking about those. It's a problem-solving tool, and you'll have one problem where you've got to think about drawing a Venn diagram with 3 circles. And oftentimes, based on the information you're given, you want to work from inside out. You want to fill in what goes in the middle, what's common to all of them first, before filling in numbers for each of these regions. And again, you want to label these regions with numbers that only refer to those specific regions. For example, the number that would go here, with an example like this, would be the percentage of people that have birds only as a pet, not cats or dogs. So expect that. Here again, these formulas that we ended with before quiz, the quiz about conditional probabilities. We will use these, we will illustrate them for card examples in a minute. Again, you can think of it either way. Focus on this way of thinking of it. The fact that A and B are just symbols means you can certainly reverse their order here. This says the conditional probability that B occurs, if it is given that or known that A has occurred, is the probability of A and B occurring divided by the probability of A. An intuitive way to think about this with Venn diagrams is as follows. Again, what you could pretend, you don't have to, is that the area of each region represents, as a fraction of the whole, represents the probability of those events. I'm not going to label these with numbers. If it is given that A has occurred, if it is known that A has occurred, that means your universe, your sample space has shrunk. It's now not anything in the sample space that could occur. You know it is given that A has occurred. So you know, in fact, you must be in this circle somewhere. The circle for A. Based on that new information, what is the probability that B occurs? The formula says to take the probability of A and B occurring, what's in here, divided by the probability of A occurring. And again, if you imagine these areas as representing the probabilities, what this ratio will represent is the fraction of this shaded area right here compared to the total area of A. Rather than, if you're after the ordinary probability of B occurring, that would be the area of the circle for B compared to the total area of the box. We assume the area of the box is 1, so it's really the same as the area of B. The area of B, as a fraction of the whole, could be different than the area of this region. In general, it will be different than the area of this region compared to the area of A. This conditional probability certainly could be different, and is usually different, in fact, than the ordinary probability of B occurring. If, however, they are the same, if the conditional probability of B occurs knowing that A has occurred is the same as the ordinary probability that B occurs, that's when A and B are independent. Knowing that A has occurred does not affect your assessment of the probability that B will occur. That's independence. And we did talk about that last time, and you had some problems related to that. Let's illustrate this formula with cards here. The card example is not so much, that we need the formulas to answer questions about cards, but they illustrate the formulas. For example, we might wonder, what is the probability of getting a heart if it is given that the card you picked is red? So use your imagination here. You've got a well-shuffled deck of 52 cards, standard cards here. You close your eyes, you grab one card at random, not necessarily from the top, and you show it to your friend. Your friend says, hey, it's red. What's the probability that it's hearts? Well, we can answer it without a formula just by looking at the picture. If it's red, that means it's hearts or diamonds. 26 possibilities total. 13 of which are red, or are hearts. 13 out of 26, 1/2 would be the answer. So we don't need the formula to solve that problem, but let me illustrate that the formula does work. If I use the formula from that slide, this would be the calculation that I do. Find the probability that it's a heart and red, divided by the probability that it's red. The probability that goes in the bottom is always the probability of a given event. That's the pattern here. Well, being a heart and red means you're a heart, okay? That intersection is the same as the probability that it's a heart. 13 out of 52 are hearts and reds. 13 out of 52 are hearts, because every heart is red. The probability that's red is 26 out of 52. So the formula in this case gives this ratio. That's the division of two fractions. You can figure out what that is by inverting and multiplying. Remember that? 13 50-seconds divided by 26 50-seconds is the same as 13 50-seconds times 52 26. Invert and multiply the fraction on the bottom. The 52's cancel, leaving you with 13 26, which is the same as 1/2. Again, we could answer that without the formula. We could just look at the picture to see, yes, we've got 13 hearts out of 26 reds total. The point here is that we can still illustrate the formula. This is different than the probability of getting hearts in general, the ordinary probability. 13 out of 52 of the cards are hearts, 1/4. So the ordinary probability of getting hearts is 1/4, whereas the conditional probability of getting hearts when you know it's red is different, it's 1/2. Getting hearts and getting reds are not independent, they are dependent. If you know it's a red, that affects your assessment that it's a heart. If you know it's a heart, that affects your assessment that it's a red. A 100% chance, probability of 1. If you know it's a heart, for sure it's red. They're definitely not independent. What's an example of independent events? Getting a heart and getting a queen, for example. Probability of hearts when you know it's a queen. Well, we know it's a queen. It's got to be one of these 4 possibilities. Only one of those 4 is a heart. So when you know it's a queen, you got a 1 in 4 probability that's a heart. But that's the same as the ordinary probability of getting a heart. There are 13 hearts out of 52 cards total, but 13 50-seconds is the same as 1/4. Getting a heart and getting a queen are independent. Works the other way too. The probability of getting a queen when you know it's a heart. It's got to be one of those 13 hearts, only one of which is a queen. That's 1/13. The ordinary probability of getting a queen is 4 out of 52, which is also 1/13. More confirmation that getting a queen and getting a heart are independent. We don't have time to go into more examples. We have lots to do in short amount of time in this class. I very strongly encourage you to think about more examples to help you understand or maybe better to say believe these formulas. These formulas do work. And this is confirmation. Sometimes you really do need the formulas. Here you don't really need them. In more practical problems, you often do need them. We'll come to a practical problem right now. Let's go back to the graduate school example. So we're back to Jennifer applying to both Harvard and Caltech. We answered the questions that you see there based on her thinking that Harvard's going to admit her with a probability of 0.4 and Caltech with a probability of 0.6 and both 0.25. Here's some new questions. Suppose she opens the mail or opens her email and she finds out, hey, she's admitted to Harvard, but she hasn't been told whether she's admitted to Caltech or not. What is now the probability that she will be admitted to Caltech given this information? This is a conditional probability because of the word given. We know something. We know she's been admitted to Harvard. Conditional probability we want to find for this first new question is, what's the probability that she's admitted to Caltech, C, if it is known that, given that she's been admitted to Harvard? The formula would say, do this. Let's go ahead and get the answer with the formula. That's the formula that was on that other slide. Again, the probability that goes on the bottom is the probability for the event that you know has happened. These probabilities are in the problem statement. Her probability of getting into both is 0.25. Her probability of getting into Harvard was 0.4. That ratio turns out to be 5/8 or 0.625. A 62.5% chance of getting into Caltech if she knows she's been admitted to Harvard. Which is different than the ordinary probability of getting into Caltech, which is 0.6. These are slightly different probabilities. If she knows she's been admitted to Harvard, that increases her chances, at least based on her personal assessments, that she's going to get into Caltech, which does make some intuitive sense. Harvard thought she was a good student, so Caltech also is more likely to think she's a good student and want to admit her based on her application. What about the other way around? What if she knows she's been admitted to Caltech and wants to find the probability of being admitted to Harvard? The formula is the same, except, careful, you need to realize you are given that she's been admitted to Caltech, so on the bottom you got to put a P of C instead of a P of H. The top is still 0.25, the bottom is 0.6 now. This reduces to 5/12, and I think that's about 0.41 something, 0.4167 I think. 0.417 is her probability of getting into Harvard if she knows she's been admitted to Caltech, which is different than the ordinary probability of getting into Harvard. Again, intuitively that makes some sense because if she's been admitted to Caltech, they thought she was a good student, so maybe Harvard is more likely to think she's a good student. They're not too much different from each other, but they have to be exactly equal for independence. Although, when we use independence, we often assume independence even if we don't have full proof of it. If something seems reasonable, we use the independence rule, this multiplication rule, in many situations where we assume independence even if we don't have complete proof of it, where independence seems reasonable. That's the multiplication rule for independent events. Talked about this briefly last time. Let's talk about it some more now. If A and B are independent, meaning these two facts are true, that's what independence means. Why? Because I said independence means your assessment of the chances that A happens is independent of knowing that B happens. So if you know that B happens, if you're assuming that's true, that doesn't affect the probability. It's the same as the ordinary probability of A occurring. And vice versa. If you know A has occurred, it doesn't affect your assessment of the chances that B has occurred. This is what independence means. And I said that when A and B are independent and you want to find the probability of both of them, you multiply the individual probabilities. You can use intersection notation there as well, but again, you don't have to know that. We used independence for this problem very quickly last time. as well as the complement rule. Let's do a new example today. There are two tests for an illegal drug in a person's body. Test A has the probability of 0.98 of being positive, meaning it says they have the drug in their body, even if that's a negative for them, if the illegal drug has been used. And test B has a probability of 0.95 of being accurate, giving you a positive result saying they have the illegal drug if it is known that the illegal drug has been used. What is the probability that neither test is positive if the illegal drug has been used? Okay, that's a pretty confusing sounding question. Take it step by step, write down what you know, and write down what you want to find. Basic problem solving strategy. What we're given here are two probabilities that are really conditional probabilities because you're assuming, you see this word if the illegal drug has been used. If the illegal drug has been used. In both of those cases, you're assuming you've got a person where you know, for some other reason, maybe because they told you, that the illegal drug is in their body. The first probability is the conditional probability that A is positive. Again, positive means it says they have the drug. That's what the positive test means here. If it is given that they have the drug. E stands for they have the drug in their system. This is 0.98. There's another test, test B. That's going to come back positive if it is known they have the drug in their system 95% of the time. These are the givens. Basic problem solving strategy is to write down your givens. What do you want to find? Write that in symbols too. What is the probability that neither test is positive if it is known that the illegal drug has been used? This is tricky. What is the probability that neither test is positive? Maybe I should just do A and B here for A coming out positive and B coming out positive. Neither test being positive means A came out negative. I can represent that by A complement. A is the event that A comes out positive. A complement means the test A comes out negative. And B comes out negative if it is known the illegal drug has been used. I'm writing this in terms of conditional probabilities, but I'm realizing we don't have to think of it in terms of conditional probabilities because we're focused on people we know have the drug in their system. We're testing them. Okay? We don't know what proportion of the whole population has the illegal drug in their system. So in reality, this is a problem, a modified problem from the book. They want you to assume you're focused on people who are known to have the drug in their system. So you don't have to think about these as conditional probabilities. They do want you to assume, so I'm writing these as ordinary probabilities now. They do want you to assume A and B are independent. Can you see this okay? If I go off the screen here? Which does mean their complements are independent. Which does mean you can find this probability by multiplication. Okay? In this type of problem, even though I initially wrote it down as conditional probabilities, I took it out of the section about independence. They don't give you the probability that a randomly chosen person has the drug in their system. So we can't ultimately solve it in terms of conditional probability formulas. We're assuming we're looking at people who do have the drug in their system when we write down these numbers and when we find this number. So I don't have to think about conditional probabilities. I can think about ordinary probabilities. the assumption is these tests are independent of each other, which is a reasonable assumption to make. You know, why should these tests affect each other? Therefore, their complements are independent, therefore you can find this probability by a multiplication. And these numbers are 1 minus those numbers, 0.02 and 0.05. You see that with the camera? 0.02 and 0.05, 1 minus 0.98 and 1 minus 0.95. These are the complementary events to A and B. So it's this product that gives you the answer. And what would that be? 0.0001. Can somebody check that? Is that right? Maybe it's just 2 zeros. 2 zeros? Yeah, okay. 0.001. 1/10 of 1% chance that they both come out negative if it is known the person has the drug in their system for some other reason that they told you. Okay? So it's pretty tricky. Break it down into pieces. This was the section before conditional probability, which is sort of the hint that you actually don't have to think about conditional probability. So in general, you have to realize that on a test by the fact that I did not give you the probability that a random person has the drug in their system. There's a general multiplication rule that works whether A and B are independent or not. And it really is just taking the formula for conditional probability and solving for the probability of A and B. The formula for conditional probability, one form of it is this. If you solve this equation for the probability of A and B by multiplying both sides by the probability of B, you can write the answer this way. You can also switch around the roles of A and B and write the answer that way. These both give you the same answer. This works no matter whether your events are independent or not. It's a general multiplication rule. For the remaining time, we're going to start another topic of probability that is going to feel pretty different, but it's still related to all this stuff. It just doesn't seem like it on the surface. We're going to talk about something called a binomial random variable. This is our introduction to binomial random variables. We will certainly talk about these more on Thursday and probably next week, next Tuesday. Binomial random variables are discrete. They're going to be counts of things. I'm going to talk about it in the context of baseball. I hope that's okay. If you don't know much about baseball, I think I can basically explain the situation to you. When I was young, younger than you, really young, about 9 years old, I first really got into baseball when I was 9 in 1977, and Rod Carew for the Minnesota Twins was my favorite player. And he had a very, very good year in 1977. His batting average was .388, which is amazing, okay? Amazingly good, which means in all his official at-bats, he got to hit 38.8% of the time. What's official at-bat mean? Well, it means you're excluding things like walks and getting hit by a pitch. Okay, those are not official at-bats. So we're talking about all at-bats where he did not walk or get hit by a pitch. He got to hit a single, a double, a triple, or a home run in 38.8% of the time. It's different from getting on base. Sometimes people can get on base even though they don't get a hit because somebody else gets out. It's called a, what's it called again? Fielder's choice, yeah. Okay? So that's very good. Pretend you've traveled back in time to 1977 and are asked to assess the chances that Rod Carew will get 3 hits in his next 5 at-bats. You could pretend it's the next game. Some games you get 5 at-bats. What are the chances that he will get 3 hits? How would you solve this problem? Ideally, I'm going to try to solve this problem on the board and try to think it through with you, but for the sake of time, I kind of got to go through these slides fast. You're going to want to maybe rewatch this, think carefully about what I say, study the book, pay attention to details. First of all, it's good to list the possibilities of what can happen in 5 at-bats. He can either have success, meaning he gets a hit, or he can have failure, meaning he doesn't get a hit. Ignoring, walks, that kind of thing. These are 5 official at-bats. You can either have a success or a failure. We're going to count the number of successes. X, our binomial random variable, is going to represent the number of successes. The word success is a loaded term, right? It's a positive sounding term. Turns out you can apply binomial random variables to situations even when success is not good. And failure is not necessarily bad, okay? They're just really labels, but oftentimes the good connotation is good, at least for Rod Carew. I mean, it's bad for the other team, right? What's good for him is bad for the other team, so it's a success from his perspective. What are the possibilities? Essentially, this is your sample space. Yikes, look at all those things. Don't write them all down, okay? I took the time to list out all the possibilities. Little s stands for success, little f stands for failure. Capital S is the sample space. There are 32 possible things that can happen. This is the one where he gets 5 hits out of 5 at-bats. This is where he gets 4 hits out of 4 at-bats, but that can occur in 1, 2, 3, 4, 5 ways. He could get 3 hits out of 5 at-bats, excuse me. In how many ways? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. He could get 2 hits in 5 at-bats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways to get that. 1 hit out of 5 at-bats, 1 S and 4 Fs. 1, 2, 3, 4, 5 ways to get that. Or all 5 failures, he doesn't get a hit, he goes 0 for 5. However, you've got to be careful in thinking that you can just say the answer is 10 out of 32, 5/16, because there are 10 ways of getting 3 successes and 2 failures out of 32 possibilities total. That's not the right answer. The reason is because these events, these outcomes, are not equally likely. They would be equally likely with coin tosses, where the chance of heads and tails are the same, 0.5. But he has a better chance of failure than he does of success on any given at-bat. So, for example, he's more likely to get 5 failures, go 0 for 5, than he is to get 5 successes and go 5 for 5. That should be intuitive, okay? Since the chance of failure is higher on any individual at-bat. Therefore, you cannot do what I just said. You cannot do 10 out of 32. You've got to do something different. What is the different things you have to do? Well, based on an assumption of independence of each at-bat from what happened previously, which is a little bit of a dubious assumption. You know, there's a psychological factor. Oh, I struck out 4 straight times. That makes me afraid. I'm going to strike out this next time. Maybe you do worse. Or maybe the pitcher is tougher the next time. So we assume independence. His current at-bat is unaffected by his previous at-bats. It turns out the probability of getting one individual outcome where he got 3 hits, like this outcome, success, failure, success, failure, success, a hit, then a non-hit, then a hit, then a non-hit, then a hit, by multiplying the probabilities of each of those individually. Each of the successes has probability 0.388. Each of the failures has probability 0.612, 1 minus 0.388. That product is going to give us our assessment of the chances that he's going to get this particular run of successes and failures. It's really independence. I'm assuming independence. It's really the multiplication rule extended to 5 things instead of just 2 things. However, that's not the same as the probability of getting 3 hits. Because 3 hits can occur in 10 different ways, there are 10 outcomes with 3 successes and 2 failures. So you actually have to use the addition rule to add this number to itself 10 times. That's the addition rule. Adding the same number to itself 10 times is the same as multiplying that number by 10. So in fact, our assessment of the probability of getting 3 hits and 5 at-bats is 10 times 0.0219, which is 0.219, or about 22%. And I went ahead and before class and I looked up his data, and I'll share this data with you, of his 1977 season, his game-by-game logs. And if I recall correctly, there were 44 games where he had 5 at-bats, and in about 20% of them he had 3 hits. So this came out pretty good. Okay? Out of every 5 games where he gets 5 at-bats, you can expect about one of them, about 20%, to have 3 hits. This is all related to something called binomial coefficient. Give me one more minute here. Related to something called a combination. I'm assuming you've heard about combinations in the past. Factorials, n choose k. That's something that most high schools do teach in pre-calculus often. That's something that's necessary for helping you compute these binomial probabilities. We'll go into more details next time. It's also related to something called Pascal's triangle. I hope that rings a bell as well. And we'll be able to relate these to why they're called binomial coefficients related to expanding binomials, okay? You gotta study this if you're gonna understand it. We will go over it more next time, but it takes work, right?